We are Juan Diego Guzman and Cristobal Sanchez, and today we're going to explain single slit diffraction. Single slit diffraction is when you shine a light through a small slit. Diffraction occurs when the reflection of light, acting as a wave, creates constructive or destructive interference. When the reflection hits the original line of light, constructive interference is created, thus the bright spots in the image. But when two reflections hit each other, it creates destructive interference, thus the dark spots.
What's actually happening here? So what I have is I have a single light source, and this source is projecting towards a slit. Now this slit produces monochromatic light. Perfect. Now, as we know from the idea of Huygens principle, at every single point in this slit we get a wavelet, so we get light being projected in circular motion. And what happens is if we take this light and allow it to project out to a screen at a set distance away, we get situations of having both constructive interference, that we get the bright areas, and we get destructive interference, where we get the dark areas. A really important graph which you're going to have to be able to produce would be the angle away from the center and the intensity distribution curve. So this curve on the far right hand side is something that you're going to have to reproduce. Now, what this shows is that bright central area, and then it shows how the intensity dips away as we see fringes, and this carries on further and further. The further out the fringes are, the less the intensity, until we can't make out these at all. Starting over, the distance between the edge of the slit and position Y is seen to be that of one wavelength. Okay. The distance between Y and point P is equal to the distance between the other edge of the slit and point P. Now you may be thinking that seems strange. If it's one wavelength difference, surely that would cause them to be constructive interference. However, we've got to remember about all of the other light which is reaching this point. And as it turns out, if we have this situation, the average difference, so in the center here, is actually only half a wavelength. And if it's half a wavelength difference, that causes destructive interference. Now, if I look at the angles here, as it happens, my first angle, angle theta 1, is equal to the distance, wavelength of the light divided by B. This is given by IB, so this is the standard statement. Now, as it happens, angle 2 is equal to, or using the small angle approximation, is equal to F divided by D. F is the distance between the slit and the screen divided by D. Now, as it happens, angle 1 and angle 2, due to small angle approximation, can be considered to be the same value, which is why I haven't got 1 and 2 subscripted on these two features. Now, that means that you can therefore work out that the distance between the central maximum and the first minimum should be equal to the multiplication of the distance to the screen multiplied by the wavelength of the light divided by the width of the slit. Now, you're not given this by the IB. You're given the earlier value, so you always have to think about that, and you'd have to explain it potentially using a diagram. Okay. So let's put this in.
Depending on the varying angles of the diffracted light, there is constructive interference and destructive interference. When the angle is 0 degrees, all of the light rays are on phase, and therefore the center wave seems the strongest because of the constructive interference. Other waves that are out of phase generate the black spots through destructive interference and the light spots through constructive interference.